So, hi everyone. This is my final year 6 presentation, which is also the NC2 course or the Scientific Computing Research Seminar course. And I'm going to talk about solving the quasi-normal mode wave equation in modified gravity theories using the discontinuous Galerkin method. So to begin with, we'll start by covering some basics of general relativity, which forms the physical background of our problem. So we start with the building blocks of GR, where we have a space-time, which is basically a collection of points which are given the name x nu, and these x nu like label all events in the space-time. After that, what we do is we define a metric, a quantity g mu nu, and this quantity tells us about the distance between the two events in the space-time. Now, once we have defined the notion of a metric, uh, when we are given a physical system, what we can do is we can solve for this metric from the Einstein field equations, as you can see on the screen here, given by g mu nu equals to 8 pi g by c power 14 mu nu, where c and g are the constants. G is the Newton's constant and c is the speed of light. So in the image here, we can see actually examples of different kind of space-times, where the first image here, if you can see my cursor, is the flat space-time. And this is how masses, for example, the Earth or the Sun, actually curve the space-times. Similarly, in the last figure, you can see how different objects like the Sun, the neutron star, and the black hole are actually curving the space-time in a different manner. And so in our work, the objects that we're interested in are actually black holes and gravitational waves. So the Einstein field equation that we saw in the previous slide, it happens to be quadratic in g mu nu, the metric. So once we try to linearize the Einstein field equations, we get gravitational waves as the solutions of those Einstein field equations. Now, physically, what happens is when there are two objects, for example, a black hole and a neutron star, or two black holes, when they're orbiting each other, they're accelerating. And that is when gravitational waves are produced from them. So we are actually interested in trying to observe this gravitational radiation from these binaries of black holes, which are like orbiting around each other. Now we want to develop the notion of stability of a space-time and what does it mean. So, for example, we want to answer the question of stability under what? So, for black holes, if we want to, let's say, observe them using astronomical techniques and so on, we want that their space-time should be stable or they should be stable entities. Now, what does this mean? This means that if, let's say, we are perturbing the system or the space-time of the black hole using an object, let's say a planet or some other object is like falling into the black hole, we want to know what happens after this event has occurred. For example, what happens after the large object like a planet falls into the black hole? So is the resulting space-time completely different? Or like what properties does the resulting space-time have? For example, like does it have different parameters? So is there a different kind of a black hole which forms after this planet falls into it, or so on? So this picture actually summarizes it in a very nice way, where we can see that there is the bigger black hole, it gets perturbed and it sort of vibrates, and then we want to know what happens after that. Now, these perturbations actually satisfy this kind of a wave equation, and we have seen a very similar form of the wave equation from Maxwell's equations of electrodynamics, where the electric fields and the magnetic fields obey a very similar equation. Obviously, the difference being here, there is a V of R potential, which we will talk about at length uh, in the next few slides. So, and we know that the solutions of a wave equation are like waves or oscillations, and the solution is actually can be written in this form, where there is a e power minus omega t dependence, and this omega has actually a real part and imaginary part, and the imaginary part is what determines the amplitude or the decay of the oscillations. So what we want to know is if our space-time, which is like obtained from some underlying theory of gravity, for example, loop quantum gravity in our case, we want to know if the space-time is stable or not. So here comes DG method into the picture. And so what is the DG method? It's basically a high order accurate method for solving partial differential equations. So the Einstein field equations that we saw in the previous slides, they were actually like coupled PDEs, and we eventually want to solve them. That is why we resort to these DG methods. And what happens here is that we have a very large computational domain, and we divide each of the computational domain into elements. And then what we do, we approximate a local solution on each element, and then finally take a direct sum to get the solution on the whole domain. This is what we can see in the expressions here. Psi k is the local solution, and when we direct sum that, we have the complete solution over the whole domain here. Now, in the so a reason for using DG methods is that they are local to the generating element, and so what becomes simple is that each element only needs information from its neighbors. So like it only needs to obtain some boundary data, and it is good to go. And the compact form of the DG method actually is like well suited for like parallel computing platforms. It is scalable, and parallel computing methods can be readily used to like increase the performance. And we'll see that it's particularly suited because we are going to do large scale time dependent computations for analyzing the tail behavior of the waveforms that we are going to get from solving the the wave equation. Now, the QNM wave equation actually comes from solving the Klein-Gordon equation that you can see here. It's basically a equation which comes from the from Lagrangian, you can say, and it basically governs the behavior of a scalar field in the background of a space-time, G mu nu. And once we have the equation, what we do is we perform a traditional separation of variables and try to simplify in a way that we separate the angular part and separate the radial or the time part. This is basically a spherical harmonic decomposition, which is a traditional method in mathematical physics. So once we do that, we notice that our metric has certain symmetry properties. For example, it's spherically symmetric, and all the components, for example, AR and BR and all, they are all time independent. So once we use all these ingredients, the upshot of all of this is that we get a wave equation of this form, which we already saw earlier. And this is what we try to solve. This is the QNM wave equation. Notice that here there is R star, the partial derivative operators, but there is a dependence of R in the potential. So we will actually come to what this means. But for now, the relation between R star, which is also known as the tortoise coordinate, and R, which is the radial coordinate, is given by this, where we have the formulas for AR and BR given to us, which appear from the modified theory of gravity. And we also have the formula for V of R, which depends on the metric coefficients AR and BR. Now, once we do that, we come to the conversion of coordinates. So the conversion of coordinates is required. For example, like we saw that in the PDE, the derivative operators are in terms of R star, but the potential is defined in terms of R. So when we come to numerically solve this equation, what we want to do is we want to make our grid in X, and we want to X meaning R star, and we want to convert R star to R and then form the potential there. So the analytic conversion or the analytic formula for going from R star to R can be seen here in this formula here. Here 2f1 is the hypergeometric function. So once we have this coordinate conversion, we can hope to write V of R as a function of R star. This is a dependence of R versus R star. We have noted down some observations. For example, like when R star is like decreasing towards minus infinity, the radial coordinates goes towards the horizon. So when the tortoise coordinates is very small, in the sense that it is towards negative infinity, the radial coordinates gets very close to the event horizon radius, which happens to be 1 in our case. So we have plotted two cases for one the modified gravity one and the Schwarzschild one, which is the traditional case. And we see that when we change the epsilon parameters, they both converge to the Schwarzschild case. Now, this is the non-trivial term in the wave equation, the potential V of R. And this is the formula that we get. We get this obviously by substituting a of r and b of r, the metric coefficients. So here in the plot, we can see a dependence of v on r, and uh, it's quite visible that uh, the radial coordinate r, when it approaches 1, v becomes 0 there, which can also be verified from the formula itself. Now, what we do is we use r star, we we produce r from it, and then we plot v of r as a function of r star. So this dependence is important, and we use this in our code to solve the uh, partial differential equation. So to generate the ring down waveform or psi, as you can see in the expression here, what we do to numerically do this, we reduce this second order equation into two first order equations. And for doing this, we introduce two variables pi and phi, the two fields which have been defined in terms of psi in this way. One is a partial derivative with respect to time, and the other is with respect to r star. So here, the pi field or the derivative with respect to time field is called the momentum of the field psi. So once we have that, what we do is we integrate the final set of equations del psi by del t, del pi by del t, and del phi by del t, which have been given in the form here numerically. And for doing this, we use the DG method. Now we can do this using two types of initial data because we are integrating in time. We want initial values in time of the fields psi, pi, and phi. Now the two types of data are referred to as, one is generic initial data, where the both psi and pi fields are non-zero, whereas in static initial data, you have the psi field as non-zero, but the pi field as zero. Basically, the momentum initially is 0. So once we do that, we can produce the ring down waveforms. And to do that, we have to choose some initial conditions for psi, which we take to be the Gaussian waveform, and some initial conditions for pi, which we take to be the spatial derivative or of this form. This is particularly an example of a generic initial data because pi and psi both are non-zero. Similarly, we can also change the parameters a, mu, and sigma because they, in a way, characterize the Gaussian, the amplitude or the spread of the Gaussian. Note that we emphasize on this point that the potential is dependent on r, whereas r depends on r star and epsilon. If we go back a few slides, we see the dependence of r on r star and epsilon. So we use the conversion coordinate, conversion routine there. And we also choose some specific values of L and epsilon to solve the system. So once we choose this, we are able to solve for the wave function psi from the PDE using the DG method. Now what we want to plot is psi versus time. So what we have to do is basically extract the waveform at some particular value of r star. So then what we would eventually get is basically psi as a function of time. And that is exactly what we plot here. So if we see this is for the L equals to 0 case, and we see that there are initially some oscillations and then a long decaying tail. So this is a log, this is a semi-log plot of log psi versus time. And so we notice that in the initial stage where the oscillations are there is called the ring down stage. We can see a similar plot for L equals to 1, just that there are a lot more oscillations now in the initial stage. And then a decay in amplitude, we see a decay in amplitude. Similarly, for L equals to 2, the rate of oscillations increases in the initial stage, and in a way, the frequency of oscillations, and then we get also a nice tail which goes down as we move later and later in time. So the same observations can be seen here that we can, like L increases and the frequency of oscillations also increases in the ring down stage. Now the waveforms have tail because we see in this images that towards later times they have tail-like features. So what do this mean? So when we try to solve the wave equation in curved backgrounds, for example, we use G mu nu, which is not flat space in our case, and we also have a potential term. We notice that the waveforms or the solutions of the PDE, the wave equation, they develop tails. So they have a decaying stage, decaying late time stage. And what we also know is that these the massless fields which we are actually simulating, so their late time behavior in a black hole space time is actually given by a power law behavior at late times. So for the generic initial data, we have the dependence on time as minus 12 plus 3. Well, L is the multipole number again. We saw in the previous graphs the dependence of L equals to 0, 1, and 1 and 2. And similarly for static data, we have minus 12 plus 4. What we want to do here is try to verify this exponents 12 plus 3 and 12 plus 4 numerically. So we calculate alpha here, as you can see, in a way which is called the rate of decay, and we try to calculate alpha numerically. To do this, we calculate the logarithmic slope, and we see that the tail actually approaches alpha equals to minus 5, which is what you get if you put L equals to 3 in the generic data. So this is the generic data case, and we see that the modified gravity one lies above the Schwarzschild one, which is a good thing in the sense that it decays slower and hence it's easier to observe. A better fit can obviously be uh, obtained by you running it for longer time. Similarly, in this case, or the L equals to 1 case, we see that it sort of approaches minus 6, which is what we want. The 2L plus 4 case, minus of 2L plus 4 case when we put L equals to 1. So this is what we get, and we see that it actually agrees with theory. Also, in this case, modified gravity one lies above the Schwarzschild one, meaning that it decays slower. So in a future work, we try to calculate the source term, basically the right hand side of the PD, which is essentially 0 right now, and that would actually model a test particle in the background space time, because right now we just have one black hole at the center and nothing else outside it. And then we try to solve the QNM equation with this source term, and then we try to calculate some observables uh, like gravitational wave energy flux at null infinity or very far. So that would conclude my talk. Thank you so much.